everyone, my name is Alec Kaluza, and this is my video presentation on Lab 4 for Physics 2212. To begin, the purpose of the lab was to predict and observe circuit behavior using the simulator we were given. Some essential physics principles were the conservation of energy and charge, known as the loop rule and node rule respectively, as well as Ohm's law. My predicted findings for the first circuit of this lab were that I2 and I1 were equal to 0.0204 amps, and my work is here on the right, so if you are watching, feel free to pause, take a look to understand how I got these values. Moving into the first circuit of this lab, the in-series circuit, it contained two batteries, two resistors of different resistance, and some ammeters and some wire. My prediction, as stated on the first slide, was 0.02, and the actual, as you can see on the image here on the right of the circuit, was also 0.02, which was good. Then when I replaced the voltmeter with the ammeter at the different parts of the circuit, both replacements read 3 volts when the proper wire placement was put, as you can see here. This is the EMF of the circuit, since the two batteries are 1.5 volts each, adding up to 3 volts. The voltmeter isn't considering the resistors currently because there is no current flowing through the circuit, and the potential was positive because of the current flow in terms of how the wires were adjusted if the circuit were to be complete. And you can see the two different situations here on the right. Then we had to find the potential difference across the circuit at various points as demonstrated in the diagram. I created a chart here just to show between what points what the potential difference was. So across the two batteries there was a potential difference of 3 volts. Across the first resistor of 47 ohms, there was a potential difference of negative 0.959 volts. And then across the second resistor of 100 ohms, there was a potential difference of negative 2.041 volts. From this, I created the final chart here, and these potential differences do sum up to 0, which goes accordingly to the loop rule that we have learned. Then, creating an ammeter in parallel with the 100 ohm resistor, as can be seen on the photo on the right. The ammeter reading changes for the current from 0.02 amps to 0.06. This is because the current becomes split at the moment it reaches the 100 ohm resistor, and it decreases the effect of the resistor on the current flow in the circuit, thus increasing the current flow slightly. Recalculating the resistance for various parts of this first circuit using the current found initially as 0.02 amps, and using the delta V found in the diagram and chart slide. Some new values for the different resistors were 47.95 ohms for the 47 ohm resistor and 102.05 ohms for the 100 ohm resistor. The resistance of the wire and the ammeter remained at 0. Moving on to the second circuit, the RC circuit for this lab. The first one contained a 10 ohm bulb, and the aim was to charge and discharge a capacitor and see how long it would take. The time to charge for this specific circuit was 5.58 and discharge was 5.73. The photo on the left demonstrates the charging, and the one on the right demonstrates the discharging. I decided to include an ammeter just so I understood the current flow at the time of the charging. The current would always approach 0 in both the charging and discharging situations, so it definitely helped me in terms of pausing and starting at the right time. Similarly, for the second RC circuit, we had a 20 ohm bulb, and similarly, the time to charge and discharge were fairly close, but they did take longer because of the larger resistance in the bulb. The time to charge was 13.17, and the time to discharge was 13.05. Same photos. On the left we have the charge photo, and on the right we have the discharge photo. Then for the time-dependent voltage, I used a 30 ohm bulb, and the equation obtained from the data here that I put into Excel and plotted was that the equation was y equals negative 0.1668x minus 0.01, and the slope is negative. We know that the slope is negative 1 over RC. So calculating RC from this equation, I found that RC was 5.995, and the actual RC from the circuit was 6, so I was happy with these results as they were very close to what it should be. And on to the final questions of the lab. If we just used a real ammeter instead of a simulated ammeter, what would the difference be? So some real ammeters have minimal internal resistance, which means we would have to add the potential difference component into our loop rule equation, meaning that the current value of the circuit would change. And if we were using a real battery to charge a real capacitor with no resistor in the circuit, how quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? In real life, it would not happen as quickly. It would probably take a little bit longer because wires do have very minimal resistance, which would delay the charging of the capacitor a little bit. In our sim, the wires have zero resistance, thus charging our capacitor faster. That is all. Thanks for listening.